Off everything.
Okay, I'm
Thank you for being here this morning. We'll get started in a couple minutes. Faye, hi, thank you for being here. We're just about to get started. Okay, great. It's the top of the hour. We still have people joining, but for the sake of not going over time, we're going to get started. So hello and welcome to all. We're so excited to have over 400 attendees enrolled from at least 70 countries spanning 6 continents here today for our first InVEST virtual workshop, Intro to InVEST, brought to you by the Natural Capital Project, or NatCap, at Stanford University. We hope all of you and yours are doing as well as possible given the current global pandemic. While the need to make these workshops virtual prevents us from meeting in person, we can potentially reach many more of you than we would be able to face-to-face, and with far less travel-related carbon emissions at that. We'd like to let you know that a recording of this webinar and the slides we present today will be available on our virtual workshop webpage following the event. I'm Jesse, your host. I'm a GIS analyst with NatCap, and I'm grateful to be joined today by a talented team of natural capital experts. Charlie, Ginger, and Stacie are our main technical presenters today. Lori and Fattin will be managing your questions and comments, and Jade will be curating and selecting some of those to pose to our presenters verbally for answering on air. I'll get to our schedule in a moment, but first, please pay attention to this important request. We ask that you only use the question and answer box to submit questions related to NatCap, ecosystem services, InVEST, or other webinar content. Be sure to type the name of the presenter to whom you intend to direct the question. Please reserve use of the chat box for logistics or to seek technical assistance related to accessing or participating in the webinar. That's question and answer box for webinar content, chat for issues with the webinar itself. We are anticipating that we will not be able to answer all questions submitted today due to time constraints. However, we will be compiling all unanswered questions and following up with answers from our NatCap experts via email. Also, feel free to email us anytime at investsummer2020@gmail.com. After this introduction, Ginger will present an overview of InVEST Sediment Delivery Ratio Model, or SDR. We'll then have a 5-minute break before Stacie presents an overview of InVEST Coastal Vulnerability Model, followed by Charlie, who will present on communicating results through data visualization. I will wrap up, and then we ask that you please stick around to take our post-event survey. Ginger, Stacie, and Charlie will each use the final 10 minutes of their respective sections to answer some of the questions you submit. We want to keep you as engaged as possible, so we'll have several polls for you to participate in, and here's our first one.
Greetings all, this is Lori. The first poll is, have you completed NatCap's new MOOC released earlier this month? Some of the answers could be yes, I am enrolled but not have completed yet. No, I have not yet enrolled but I plan to. Or no, I am not planning on it. Let's give you a few more minutes before we end the poll.
And I'll just say, if you're unaware, MOOC stands for Massive Open Online Course, and you can find ours at edx.org. That's edx.org. And just like this webinar series, it is free.
Thank you, Jesse. And we're going to end the poll in 5, 4, 3, 2, 1. And I'm going to share the results. It looks like we have 47% of you that have not enrolled but plan to take it. So thank you so much.
Great, thank you, Lori. NatCap is centered at Stanford University's Woods Institute for the Environment and is made up of partnerships with the Chinese Academy of Sciences, the University of Minnesota, and the Stockholm Resilience Center. NatCap advances new science together with, inspired by, and implemented through the Nature Conservancy and World Wildlife Fund. Beyond these core partners, we maintain important partnerships with more than 150 organizations, governments, and institutions worldwide. We are an interdisciplinary team of academics, software engineers, and real-world professionals, all working to make valuing natural capital easier and more accessible to everyone. NatCap recognizes that Black lives matter. We envision a world where all people thrive, but this cannot be achieved without equity, justice, and respect for one another and the environment that sustains us. We recognize the many ways systemic racism shapes our society, and we stand to fight against it. We are listening, learning, evaluating our own approaches, and working for change. The Natural Capital Project pioneers science, technology, and partnerships that enable people and nature to thrive. We work to integrate the value nature provides into society into all major decisions. Our ultimate objective is to improve the well-being of all people and nature by motivating greater and more targeted natural capital investments. Through cutting-edge ecosystem services science, we map, measure, and value nature's benefits to people. Through innovative technology, like our InVEST software platform, we harness global environmental data to provide decision makers with actionable information for policy, finance, and management decisions. Through our partnerships, we produce tailored results informed by local knowledge. We innovate and build capacity with communities worldwide, engage key leaders, and collaborate to reform institutions so that private short-term goals will more closely align with society's long-term goals. In terms of the science, we know that when properly managed, ecosystems yield a flow of services that are vital to humanity, including the production of goods like food, life-supporting processes such as water purification, life-fulfilling conditions like aesthetics and opportunities for recreation, and the conservation of options for the future, such as genetic diversity. Despite its importance, the stock of assets known as natural capital is poorly understood, scarcely monitored, and in many cases undergoing rapid degradation and depletion. The diagram shown here depicts the steps in an ecosystem services assessment. The tools that we've developed are designed to be helpful at different stages of this process. Ginger will go over this in detail in the next section. InVEST is NatCap's flagship software product. InVEST stands for Integrated Valuation of Ecosystem Services and Trade-offs. InVEST is a suite of free, open source software models used to map and value the goods and services from nature that sustain and fulfill human life. InVEST uses a simple framework delineating supply, service, and value. Supply represents what is potentially available from the ecosystem. For example, supply can be the wave attenuation provided by a particular location's density of mangrove forest. Service incorporates demand, such as reduced coastal erosion and flooding, and thus uses information about beneficiaries of that service. For instance, where people live, important cultural sites, infrastructure, etc. Value includes social preference and allows for the calculation of economic and social metrics like number of people affected or avoided damages from erosion and flooding. Through NatCap's approach, InVEST can enable decision makers to assess quantified trade-offs associated with alternative management choices and to identify areas where investment in natural capital can enhance human development and conservation. The modular design of InVEST supports inclusion of multi-service assessments, providing an effective tool for balancing the environmental and economic goals of diverse entities such as governments, nonprofits, international lending institutions, and corporations that all manage natural resources for multiple uses. The toolset includes distinct ecosystem service models designed for terrestrial, freshwater, marine, and coastal ecosystems, as well as a number of helper tools to assist with locating and processing input data and understanding and visualizing outputs. InVEST simple models have relatively simple data requirements and are spatially explicit, using maps as information sources and producing maps as outputs. InVEST returns results in either biophysical terms, such as tons of carbon sequestered, or economic terms, like net present value of that sequestered carbon. The models are applicable across the globe, and the spatial resolution of analyses is flexible, allowing users to address questions at local, regional, or global scales. There are 27 InVEST models with more in development. That's currently. So knowing how to use geographic information system software such as QGIS or ArcGIS is crucial for preparing spatial inputs to InVEST models, viewing and understanding model output, and post-processing the output to provide meaningful results. But running the InVEST models themselves does not require a GIS. Each of the tools is an independent application. You should be aware of and rely upon these three important resources for InVEST documentation and support. The InVEST user guide is an invaluable resource for learning not only about the science and theory behind each model, but also how to use them. Access it through our website, where we have English, Spanish, and Chinese versions. Each model's chapter contains important information, such as an explanation of the science, methods, and equation behind each model, input data requirements, a description of each model output, and global data sources. So be sure to read the user guide carefully before using a model, and then use it as your first resource for answering questions. If you have questions about InVEST or problems that the user guide does not help with, another great resource is the NatCap forum. Find it at community.naturalcapitalproject.org. It is a natural capital community and support site monitored regularly by our engineers, data analysts, and scientists. There you can search for information, post new questions, and connect with ecosystem service practitioners around the world. Finally, sample data is available for each model. You can elect to install sample data when installing InVEST. The files are also downloadable through our website. If you're new to an InVEST model, running it with sample data is a great first step to gain experience using the interface and seeing what the inputs and outputs look like. The URL for downloading the InVEST installer and associated sample data is naturalcapitalproject.stanford.edu/invest. We asked that you install InVEST prior to this webinar. Before I pass it over to Ginger, we have our next poll question.
Thank you, Jesse. Our next poll question is, we're interested in getting a better idea of your background. Please let us know what field you're working in. The options are terrestrial context, marine context, both, other, or new to ecosystem services. Give everybody a few minutes to answer that. And I'll end the polling in 5, 4, 3, 2, 1. Wow. Okay, I'm sharing the results. It looks like 55% of you are in the terrestrial context. Thank you.
Thanks, Lori. That's very interesting to see that result. I think we thought it might be more distributed evenly. So next up we have Ginger. Ginger is a GIS programmer analyst with NatCap, and here she is with an overview of InVEST's SDR model.
Hey, thanks, Jesse. I'm really excited to talk with you all. So we are almost up to 300 participants, which is amazing, fantastic. Yeah, the virtual context definitely has its limitations, but in no other context would we be able to talk with this many people. And I see people from Egypt, Spain, Colombia, Mexico, the United States. This is really awesome. So very excited to talk with you all. Let's see. Okay. I'm going to be talking today about water quality. So this should be an interesting topic for most of you, since we have a highly terrestrial crowd. I'll be talking through a case study conducted by some of my colleagues, and also doing a very light introduction to the sediment delivery ratio model, which Jesse mentioned. SDR is a popular model from the InVEST suite related to terrestrial water quality. Our mission at the Natural Capital Project, or NatCap, is to shine a light on the connections between people and nature. And we believe that when the contributions of nature to society are more clearly accounted for, leaders and decision makers are empowered to make decisions that are better for both nature and people. Stacie showed something similar to this. So the InVEST model suite contains many models that each quantify a single ecosystem services. So here are some examples of the terrestrial ecosystem services that we have models for in the InVEST suite. For example, we have a pollination model, we have a water yield model, a habitat quality model, and later, Stacie will be talking about some of the models in the InVEST suite that are for coastal and marine contexts. Today, I'm going to be talking about a case study where we used InVEST to quantify ecosystem services related to clean water in the context of water funds. So I remember that a few of you have already studied the MOOC, the Massive Online Open Course offered by NatCap. So you already have some familiarity with water funds. The concept of water funds is based on the idea that it is often cheaper to prevent water problems at the source than it is to treat them further downstream. So a water fund uses investments in green infrastructure and uses natural systems to trap sediment and regulate water. These investments are paid for by water consumers downstream to support water and soil conservation measures upstream in the watershed. So this case study was to study the business case or the economic case for implementing a new water fund in the Upper Tana Basin of Kenya. This region is important for many reasons. Just north of Nairobi, you can see it's home to 5.3 million people. It provides 95% of the water supply for Nairobi, the capital city, and half of the hydropower supply for the entire country of Kenya. But in the last few decades, along with development of this area and conservation of forests and wetlands to agriculture, sedimentation in the water supply has become a serious problem. Sediment coming down the watershed reduces the capacity of reservoirs and increases the costs for water treatment. And we know that the challenge of ensuring a clean and reliable water supply is likely to grow in the future as climate change brings increasingly unpredictable rainfall. In this context, NatCap was part of a large team brought together to study the possibility of implementing a water fund to address these sediment issues. And if implemented, this would be the first water fund in Africa. I'm going to use this figure that Jesse already introduced to step through the structure of this case study. This figure is also in our MOOC, and it illustrates a generalized approach to ecosystem services assessment. And it moves from building the project foundation through scoping and building the right kind of team, all the way through data collection, scenario development, analysis, data synthesis, and all the way to reaching out to stakeholders and decision makers. Also, it includes lots of planned iteration along the way. So I'll step through each of these steps and tell you about how they played out in the Tana Water Fund case. So first, starting with project scoping, this is where we lay the foundation for a successful project, build the team, and make a plan for successful analysis. First, the scoping phase for this project started with a really clear decision that was to be informed by the modeling study. In this case, investors needed to know, is there a business case for creating a water fund? Is it worthwhile for them to spend money on upstream water management activities in terms of the returns that they would get downstream? Next, it was important for the team to make sure that they were able to quantify the metrics that really matter to those stakeholders. to make sure that there was a match between the models that they had available for analysis and the actual type of information that stakeholders would use when making their decision. So here it was clear that information about changes in water quality, especially issues related to erosion and sediment loads, was information that stakeholders would really take into account when making their decision. Finally, the team had to narrow down their analysis to a specific geographic area of interest. And for this type of modeling, where we're interested in water moving across the landscape, it's absolutely critical that the geographic area of interest be hydrologically complete, or entire watersheds. So the team chose 3 watersheds supplying the bulk of water to Nairobi. A couple other points about project scoping and laying the foundation. For this project, it was really key to have a team with the right connections, funding, influence, local knowledge, and capacity to do both technical modeling and also scientific advice. So the team was a broad coalition of international and local nonprofits, academic, and stakeholders brought together, bringing decision-making capacity, local knowledge, science guidance, and GIS skills. So the goal with this study was to address these 3 main questions. First, where should the water fund invest its money for maximum cost effectiveness? Second, what would we expect the change in watershed services to be if those investments were made? And then, because this is an economic feasibility study, what do these watershed service improvements mean in terms of cost savings or economic impacts to downstream users and also the landowners that would be implementing these land management changes? So moving on to the next phase, the data collection phase, this is, of course, a large and important step in any assessment process. In this case, here are some of the types of data that were necessary for this project. A digital elevation model, which is a raster giving elevation of each pixel. A land use land cover raster, which gives the spatial arrangement of different land use types. And some biophysical coefficients that are in a table. You can see an example down at the bottom of the screen. These data types are really common to most of the terrestrial models in the InVEST suite. So the digital elevation model, or DEM, is really important for water-related models because that's how the model routes water flow across the landscape. The land use land cover raster represents, as I said, the spatial arrangement of different land use types, and it often goes together with this biophysical table, where each land cover type in the land use cover raster is associated with numerical parameters in the biophysical table. Jessie mentioned that we have some guidance on recommended data sources. So it's really important to us at NatCap that all of our models be useful throughout the world. It's one of our core values that it should be technically and scientifically possible to apply InVEST models anywhere in the world. So the NatCap team has worked to design models that have low data requirements and that rely on data types that are available anywhere in the world. This means you can often get started with an InVEST model purely based on globally available data without needing to collect any more detailed local data. And on our website, we have suggested global data sources for each model. We'll talk about that more later. So this can be a really great way to get started with an InVEST model, but of course, depending on your constraints and your resources and your goals with the modeling process, it can be really important to seek the most appropriate data for your application, sometimes from partners, often from the scientific literature, or sometimes developing it yourself. The next step in a generalized assessment is to build scenarios. And in this study, the scenario building phase was a very important component of the project. Because a water fund consists of an economic investment in a biophysical outcome, it was important to contrast the biophysical returns that could be expected under a range of investment futures. So scenarios are contrasting pathways to the future that can be used to illustrate the range of potential outcomes that we can expect to see in the future from different decisions made today. When it comes to modeling with InVEST, the key thing about these scenarios is that they can be spatially represented. Often they take the form of alternate future land use maps. And then these maps are the inputs for ecosystem services models that can be used to explore the biophysical outcomes associated with those different future paths. In this case, the team used the RIOS tool to come up with spatial scenarios of investment in watershed management activities at these 4 different budget levels. So these maps that you see on the screen show the different land use management activities that were associated with different levels of investment. Where you see bright colors, that means a lot of transition in land use associated with management activities. And when I say management activities, I mean things like planting agroforestry, installing grass strips, terracing, riparian management. These are activities that we expect to have an impact on sediment. And these different scenarios represent different total amounts of these activities, showing up as changes in land cover. So the next step is the analysis step, often the fun part, at least if you're a technical person. This model to quantify the ecosystem services supply that would result from each scenario. So here we use a model such as the InVEST SDR model to translate a change in land cover into a change in a biophysical metric. For example, you could use the InVEST SDR model to calculate, given an investment of $4.5 million US in management change, what would be the change in annual erosion that we would expect to see. So at this point, let's take a brief detour to learn a little bit about the SDR model. The sediment delivery ratio, SDR model, estimates annual erosion and delivery of that eroded sediment to streams according to abiotic and vegetation-related characteristics of the landscape and their spatial arrangement. The first step is that the model first predicts potential soil loss from each pixel using the universal soil loss equation. So potential soil loss is calculated as the product of 5 factors. Each of these is considered per pixel. First, we consider the slope of each pixel, erosivity on that pixel, which describes the erosive force of rainfall, erodibility, which describes how easily the soil can be removed, and then 2 vegetation-related factors, conservation factor and crop factor, which describe vegetation holding on to sediment on that pixel. And then the product of those 5 factors is potential soil loss. So from this, you can probably guess that some of the important inputs to the SDR model come from soil data, rainfall, climate data, topography, which is derived from that DEM, digital elevation model, and the crop and conservation factor are associated with land cover types, where each land cover type has a certain value for these factors. And those land cover values are contained in the biophysical table. The second step in the SDR model is to calculate delivery of that sediment from the stream to the stream. So the model computes a delivery ratio, which describes the ratio or fraction of sediment coming off of a given pixel that actually makes it all the way to the stream. And loads in the stream. And we also get an idea not only of places on the landscape that are experiencing erosion, but that are really contributing to sediment loads in the stream. As an example of how the delivery ratio is calculated, we'll look at SDR relative to this orange pixel. So the SDR, or delivery ratio, for that pixel is a function of the upslope area and the downstream retention path. So the upslope area represents the energy of water coming into that pixel, running across that pixel, and potentially carrying eroded soil off of that pixel to the stream. So if the upslope area where water collects before it reaches that pixel is large or highly sloped, then you can imagine a lot of energy arriving on that pixel to carry soil to the stream. The downslope path is the path that water follows between the pixel and the stream, so where water goes after it leaves the pixel. And so if this path is short, if it has a high slope, if there's not much vegetation on it to hang on to sediment, then you would also have a high delivery ratio. So we calculate the sediment export from that pixel in the stream as the product of USLE, or potential erosion, and the sediment delivery ratio. We do this for every pixel in the study area, and then the sum of sediment exported to the stream is just the sum across all of those pixels inside the watershed. And that is how the model arrives at an estimate of sediment load in the stream. So from that basic intro to SDR, you can probably see that the land cover raster is a very important input to the model. In this case, only after presenting initial results to stakeholders did the team realize that an important part of the watershed was not included. So they had to go back, add this new southern part of the watershed, and revise their analyses. So this is an important lesson. Don't forget to plan for iteration. Revisions will happen, and to me, they really indicate how powerful the results of an assessment like this can be for stimulating discussion and collaboration. And that discussion will lead you to new ideas to analyze in the next iteration. Okay, I would like to hear from you guys. Considering the way the SDR model represents erosion and sediment loads in the stream, which of these data formats do you think would be the most compelling way to communicate those results from the model? Awesome, I see the poll. Thanks, Lori.
Okay, so we're going to wrap it up fairly shortly. In 5, 4, 3, 2, 1, and we're ending polling. And we're sharing the results.
Okay. I see we have a very map-oriented audience. These are people after my heart. I agree. I would probably like to see a map. However, of course, the right answer to that question, of course, depends on your purposes for using the information that the model provides. Thankfully, the SDR model produces all of those forms of data as outputs, so you can choose or use all of them for different audiences. The main outputs from SDR are sediment lost from each pixel, sediment delivered to the stream by each pixel, and the model also calculates a retention index, which is a derived relative index. It's calculated as the difference in sediment export under the current land cover versus land cover consisting of bare soil. So you can think of this as the difference that vegetation makes in the sediment exported by the watershed. And all of these results are aggregated by the model up to watershed level, giving you that tabular numerical output. So returning to the idea of different kinds of data results being appropriate for different audiences, here's how the team used their model results to inform stakeholders. They used different outputs for each stakeholder groups. For example, decreased sediment loads in the stream are what matters the most to power and water utilities, because sediment loads in the water causes damage to their facilities and requires treatment. Also fills up the reservoirs of KenGen, the power utility in the region. So the most useful output, most useful information for those who care the most about sediment loads would be this change in sediment export. Contrast that with the information that's most useful to farmers or landowners in the upstream areas of the watershed. This is the same outcome, avoided erosion, but farmers don't care as much about how much sediment is actually in the stream or is delivered to the reservoir. They care about soil that's being lost from their land in the different watersheds. So this translates to changes in soil fertility, and this is the information that was most salient for the farmer stakeholder group. So those biophysical outputs, erosion, changes in erosion and changes in sediment loads in the stream, that's where the SDR model stops. That's the output that you get from SDR, that's the end. And in some cases, those biophysical outputs are the relevant endpoint. Sometimes that's the information that you need to inform a decision. But in this case, because it's a business case, it was important to translate those biophysical metrics into economic terms. So this is usually conducted outside of InVEST, where biophysical outcomes are translated into monetary benefits with an economic analysis. So here the team used a detailed economic analysis, and I would encourage you to check out the business case report, which is linked here, and I'll also help you search for it if you'd like to see the details of the economic analysis. But the outcome of that analysis was that the team estimated that an initial $10 million US dollar investment over 10 years would lead to a 21 million US dollar return to these three key stakeholder groups. So the final step in this case was to reach out, convey, communicate results, and the main outcome of this case was to communicate the results of the business case to funders who did decide to launch the water fund from the economic argument. So the Upper Tana Water Fund launched in 2015, and it was the first of its kind in Africa. The water fund provides training, resources, and equipment to 15,000 farmers in those upstream areas to keep rivers healthy, conserve water, and increase crop yields. Stacie mentioned some of this, but I wanted to reiterate that for the SDR model, and actually for all of the InVEST models, the best place to get more information about how the model works and to get a start on collecting the input data for the model is to check the documentation. So you can always read the model documentation on the NatCap website, or you can also reach the model documentation from the model user interface itself. There's a little blue hyperlink when you open up the model, and if you click on that, it will take you directly to the documentation. For each model, there is an appendix giving some suggested data sources that you can use to find data to run the model for your area. And then I'm also going to plug again the NatCap community forum, which is linked here. It's a great place to ask questions of NatCap scientists, but also of other users who are working on topics that are, you know, all over the world and often have really good advice about running these models. Last, if you would like to get a little bit more in depth about the sediment delivery ratio model, come to our next webinar on August 4th, 2 weeks from today. In that webinar, we will get a little more in depth with the details of the model, and we'll also learn about another closely related InVEST model for water quality, the nutrient delivery ratio model. So with that, I hope there are some questions. Jade, can you help field the questions?
Yes, you have a few questions. Thank you, Ginger. So there's three questions from Dan Hayes asking, in terms of percentage, how is the collection of data performed? Meaning 100% remote data or field primary data? How could you give him a little sense of what's the amount of field work versus remote sensing?
For the SDR model, so the really critical inputs are those that I mentioned, the DEM, land use, land cover, and then the erosivity and soil. I think most of the global data sources for those that we recommend are based on remote sensing, because of course they have to be raster based, so they need to cover your entire study area, and if they're global sources, they need to cover the whole world. It's not common to use field-based metrics to parameterize this model, except for maybe the conservation and P factor, which, well, those usually come from the literature, but those pertain to specific vegetation types. I think it's probably more common to use field data when calibrating the model. And that's, you know, an advanced topic that is probably best addressed by looking at some of the peer-reviewed literature related to this model. That's on our website, and you can see there where scientists at NatCap have used, you know, gauge-based sediment load data to calibrate the SDR model. That's probably the most salient need for field data.
Thank you. And the next question is, how many people roughly were involved in the Nairobi project?
Great
Hi.
question.
Do you want me to help answer that, Ginger? Hi,
Sure.
this is Stacie. I actually worked on this project. And there were a lot of partners that worked on this project. There were 3 of us at NatCap, somebody who did project management. I did GIS analysis. We had an economist as well. But then we also had partners doing hydrologic modeling at another institution, partners with the Nature Conservancy who were organizing. So probably at the core, there were maybe 7 or 8 people. But then we worked with a lot of other partners in gathering data, doing field work, and really making the project happen.
Thank you, Stacie. And then the next question is, how effective is this model when used for a shared water resource, for instance, the Nile or Niger in Africa?
So the things that this model handles well are based on topography and land cover. So this model is all about sheet or overland erosion. This model doesn't work well with landslides or gullies or, you know, like a one-time extreme rain event. So I think that might be an important limitation to keep in mind in terms of the biophysical setting. In terms of the beneficiary related information for this model. You know, I think I mentioned that everything is calculated relative to a watershed. So if there are sub-regions that you would like to analyze separately or contrast with each other, this model is really well set up to do that if they can be grouped into sub-watersheds.
Thank you, Ginger. And there's another question asking if the model has been used to quantify SDR in shallow lakes.
I don't think so. That's a great question for maybe our community forum. I don't know of applications of SDR to lakes. It's really about, as I said, water flowing over land and through streams. Another important limitation for this model is that it doesn't consider in-stream settling out or deposition. It's kind of like the model looks at sediment that is lost from a pixel and that makes it to the stream. And then once sediment makes it to the stream, it's kind of counted as exported. So that's one of the main simplifications of this model. But a great question for the community forum, or maybe even just a topic to search. There may be some posts already there.
Thank you, Ginger. Another question is, what is the criteria you use on the pre-selection process of a specific project/region?
Sorry to interrupt, but let's just have this be the last question for this section, please.
Sure.
Sounds good, Jesse.
Yeah, that's a great question. I think so. In terms of having the right capacity, and also in terms of having the project be geared towards a specific decision that is ripe for input, I think is a really important criteria. So knowing that the kinds of information that your model or analysis is going to be able to provide is relevant to stakeholders that have an imminent decision or a real chance to make a change in land management actions, I think is one of the most important criteria for choosing, or choosing situations when these kinds of models could be useful.
Thank you, Ginger.
Thanks, Jade.
Thank you, Ginger and Jade. We'll now have a 5-minute break. We're slightly behind schedule, so let's reconvene at 8 minutes before the top of the next hour. That's 9:52 on my clock here in California, so 8 minutes before the top of the hour. Welcome back. We'd like to let you know that a recording of this webinar and the slides we present today will be available on our virtual workshop webpage following the event. We remind you to please use the question and answer box for webinar content and the chat box for issues with the webinar itself. So we already got to hear a little bit from Stacie. She is a senior GIS analyst with NatCap, and here she is with an overview of InVEST coastal vulnerability model. Yeah, you're muted, Stacie.
Sorry, everyone. Okay, how's that?
That's great.
Is that? Okay, great. Sorry about that. Hi, everyone. Hope you did a little dance during the break like I did to get that blood moving. Just like Ginger talked about, the vegetation on land can play a role in helping to reduce erosion in terrestrial systems. The natural habitats that are along a coastline can also play a really big role in helping to protect the coastline from erosion as well as flooding in the event of a storm. So when storms come in, they bring high winds and big waves that can have big impacts for communities who live along the coast. So we made this coastal vulnerability model to help see the connection between natural habitats and coastal protection. And the model can help us to understand where these marine habitats can provide protection from flooding and erosion in case of a storm. It can help us see how much protection they provide, as well as where there might be opportunities for conservation or restoration that might protect coastlines and help us to build more resilient coastal communities. Now, the way the model works is to first look at the shoreline, and it takes your shoreline and breaks it up into a series of shoreline segments of whatever size you define. And for each of these shoreline segments, we will provide information about several biophysical factors that play a part in influencing coastal erosion and inundation. These are things like the geomorphology, the types of habitats that are there, and other inputs that I will look at one by one. And so what the model does is looks at that shoreline segment and what kind of habitat or geomorphology is there and ranks it on a scale from low to high about whether it is helping to protect the coastline or not. And then it takes all of these input variables and combines them into a single exposure index result. And this result gives us an idea of which places on the shoreline are more or less exposed to the effect of wind and waves. So it's important to understand that this result is a relative ranking, right? We're looking at which places are more or less exposed within our area of interest, right? So we don't know what's happening outside the area, but we do know what's happening inside. Now, this is kind of a scary looking chart, but it really encompasses how the model is working. And it's very simple, actually. The way it works is that we have all of the biophysical variables listed along this left-hand column, things like geomorphology and habitats again. And then the model looks at the different types of habitats or the different type of geomorphology. And then you decide whether those are contributing to a relatively low level of coastal exposure, meaning that they're offering a lot of protection, or whether they are contributing to a high level of exposure, meaning that they are not really providing much protection. So let's look at these one by one. The first input is shoreline geomorphology. This is a line vector input to the model that tells us what is the shoreline composed of. So if you look at the picture on the left, the shoreline is very rocky. And a very rocky shoreline like that is going to be really good at helping to reduce the impact of waves that come into shore. So people living there are going to be at much lower exposure to the effects of storms. On the other end of the scale is something like a sandy beach. Sandy beaches erode very easily, and they really offer very little protection in terms of reducing the impact of wind or waves. Okay. Now, these rankings from 1 to 5 they are given in our user guide, but they are intended to be a guidance for you or to help get you started. But in this case, it's up to you to decide how much protection these different types of shoreline geomorphology might provide. The next input to the model is relief, which is just the elevation above sea level. The input for this is a digital elevation model. And in this case, the model will calculate the rankings from 1 to 5. So places that are very high elevation, like you see in the left-hand picture, are going to contribute to a low level of exposure, because if somebody lives on the top of that cliff, they are not going to be directly exposed to the effects of waves. But on the other side of the scale, we have very flat areas that are near sea level, like this delta. And if somebody lives there, they are very exposed to the effect of waves because they are at sea level. Now, natural habitats are another input that you define. You can have a variety of natural habitats along the coast, both in the water and along the coastline itself. Something like mangroves are going to be very effective at helping to reduce the effect of both wind and waves. The roots are very good at holding in the soil. The trees themselves are very good at reducing the effect of waves as well as wind. So a community living on the other side of those mangroves has much lower exposure to the effect of storms. On the other side of the scale, there's something like seagrass, which we know slows down waves a little bit, but not nearly as much as a coral reef or a mangrove forest. So we give that a value of 4, meaning that it contributes to a higher level of exposure, but it's still helping a little bit. So you're starting to get an idea of how the model works, how it thinks about each of these inputs. Now, we also need to know just how exposed physically each shoreline segment is to wind and waves. So for this, the model takes in a global data set called WaveWatch 3 that has information about wind and waves, how strong they are, and what direction they come from. And the model will calculate the places that are exposed to the least amount of wind and the least amount of waves, as well as the areas that are exposed to the most. And it will give them a ranking from 1 to 5. The next input is surge potential. And for this, we usually consider the location of the continental shelf. If you look at the pictures on the bottom, the picture on the left is a place where the continental shelf is very close to shore. And if somebody lives on the shoreline in a place like this, they are much less likely to get inundated during a storm, right? It will have more of a bathtub effect where the waves come in but don't make it as far upshore. But in the picture of the right, the continental shelf is very far away. So the seafloor is very gradual slope, and somebody who lives on that coast is much more likely to have the impact of waves, right? So the model looks at the location of the continental shelf, and it determines the places where the continental shelf is closest will get a value of 1. The places where the continental shelf is the furthest away will get a value of 5. Now, sea level rise is kind of a different input to the model. And the thing about sea level rise is that usually, or often, we are working in a place where that's small enough that sea level rise is thought to be uniform across the whole area. So if we only have one value for sea level rise, then because of the way the model works, because it is a relative ranking model, it really won't have an impact on the results. But if your sea level rise is different across your area of interest, then you can incorporate it into the model. And of course, places with less sea level rise are likely to be less exposed, and places with higher sea level rise are likely to be more exposed. Now, we've talked so far about biophysical factors, and that's very important, but really it's only an ecosystem service if somebody benefits. So for this, we need to take the biophysical risk, which you can see in this map here is an example from an analysis that was done in all along the coast of the United States. And they looked at the coastal vulnerability of the whole coast. And this is just the southeast portion of the United States. And they took the biophysical risk and combined it with social risk. Now, this is where people come into the picture. We used census data to look at where the most people lived. And not only that, but to look at where people lived who were at higher social risk. So these are people like elders who might have problems getting out of a town in case of a storm, or poor people, etc. So they combine this information on biophysical risk with information on social risk to create maps that show where natural habitats are providing the most benefit to the greatest number of people, and particularly people who are elders or people who are poor. And we can look at this both in the current conditions and see how it changes with climate change, right? So this is a really important part of this modeling, is not only doing the biophysical modeling, but then connecting it with people. Like all of our InVEST models, this model is simple. It is a simplification of coastal processes that are actually very complex, right? Another limitation of the model that we've talked about is that the results are a relative ranking of these shoreline segments. So there is no quantitative information provided about the amount of erosion or the level of inundation, right? Also, the natural habitats input to the model is very important, but the model does not explicitly consider the quality of the habitat or the quantity of the habitat, only its presence or absence and where it's located. And then finally, as I just noted, sea level rise must change spatially, or else it doesn't really have an impact on the results. Now, I want to give you an example from a project that we are working on right now. It's called the Smart Coasts Project along the Mesoamerican Reef. And it involves partners in Mexico, Belize, Guatemala, and Honduras, where we're looking at actually several ecosystem services, including coastal vulnerability, as well as sediment that Ginger shared, and recreation. And we're looking at them in the current conditions and the benefits they provide to coastal communities. We're also looking at how climate change might impact these services. And we are modeling some adaptation strategies and looking at how they might influence these services into the future. Now, I know a lot of people on the chat have asked about input data. So I wanted to just give you an example of the kind of input data that we used in this project. And the emphasis here is that for pretty much every project you do, it's going to be a real mix of data sources. Some of it will be global, some of it may be very local, You'll get it from different organizations or sources. Something that's really, really nice about the coastal vulnerability model is that we provide a lot of global data sets that are really good to use. So it helps you get started very quickly with this model. Like you can see with habitats in this project were one that included both national data sets and global data sets. Geomorphology is actually really tough because there is no global data source that we are aware of. So what you often have to do, which is what I did in this project, which was to look at satellite maps and hand digitize what I thought the coast might be made out of. So that one is a tough one. But most of the other data sources, you can see that we use default global data that we provide, or data sources that are easily downloadable like GEBCO or WorldPop. And you can also see that there's a variety of resolutions to the data, and that's okay too. Most of our models can handle that just fine. So to look at some of the results of this, the map on the left shows the exposure index along the whole coast. The places that are in red have the highest exposure to wind and waves. The places in blue have the lowest. And if we're looking at this whole area, we can see that this northern part of Mexico and the Yucatan really shows up as a place of highest exposure. And one of the reasons for this is because of the natural habitats. So if we look at this other map on the right, we can see that there is a lot of natural habitat along the coast, but relative to the rest of the coast, up here in the Yucatan, there is relatively little natural vegetation. And what is there is mostly seagrass, which, as we saw before, provides a very low amount of protection. So this is emphasizing the relative ranking emphasis of this model, right? The places with lower amounts of habitat are likely to show the highest level of exposure. And then further down the coast, we see places of lowest exposure, and we can look at just how much the natural habitat is there in terms of coral reefs, especially, and mangroves are very effective. Now, another thing the model does for us is to do one run where all of our natural habitat is intact, and another run where all of our natural habitat is removed, so that we can see the difference. What happens if we lose our natural habitats along the coast? So the left-hand map is the same coastal exposure for the current conditions. The map on the right shows the difference in coastal exposure if we remove all the habitat. Now you can see that so much of the shoreline now is in this highest category of exposure because it has lost its habitat, and the people who live along the coast are no longer receiving that level of protection. And this is more important in some places than others. There are places like around here in Cozumel that still have a relatively low level of exposure. Okay. So this is important because each area of the shoreline may be impacted differently. And then, of course, we want to bring people into the picture. The model also includes an input for population. So it will tell us how many people live near each shoreline segment. And if we add up the number of people within those areas of highest exposure, then we can see that with habitat, the number of people at highest exposure is actually around 1,000 people. Okay, it turns out there aren't that many people living up in the Yucatan and live along the coast. But if we take away all of the habitat, now we have more like 19,000 people who fall into that category of highest exposure, right? That's really significant increase. And then the other thing we wanted to do in this project was to focus on marine protected areas. And if we remove all the habitat from the marine protected areas, now we see that we've gone from about 1,000 people to about 4,000 people of highest risk. Right? So this part is really important in connecting it with people, because what we want to do with this project is to help create more resilient communities and more resilient ecosystems along this coast. Now, since Charlie is going to be talking about communication, I wanted to emphasize that we had for this project a lot of communication with our partners, and many iterations are still going on. We have weekly meetings with partners to get feedback. We have workshops where we invite a lot of stakeholders, and there we present some of our current findings, and we ask for feedback. And people may say, oh, I have better data for this, or that part of the coastline doesn't look right. I don't think those results are right. So we talk with them, and we go back and we do another iteration that brings us closer to a product that's really effective and that everybody really feels good about. These maps that you see are actually from a workshop where we sat down and people drew on maps to tell us where different things were happening along the coastline now, and as well as in the future. What might that future look like? And this gets incorporated into our analysis. So be prepared if you're doing a really good analysis. Be prepared to have a lot of interaction with your partners, and be prepared to do multiple iterations in order to get a better and better analysis result. Okay, that's all I wanted to say about that. Jade, do we have any questions?
Yes, we do. Thanks, Stacie. So the first question is, how are the scores combined into a ranking? Is it a decision tree or via summation?
It is a very simple summation. You can look in the user's guide. The equation for that is in there. They are weighted equally, and they are summed and calculated in a very simple way. There's no decision tree or weighting or anything like that.
Okay, great, thank you. The next question is, does the InVEST model compare natural barriers with artificial structure? And if not, do you have a suggestion on how to compare them?
The model does not compare them. You can use something like seawalls as an input to your geomorphology and provide information about how effective you think that is. But the model is really focused on natural habitats. So it is going to be telling us more about how natural habitats may be effective, and not so much about infrastructure.
Thank you, great answer. The next question is, does the coastal vulnerability model accounts for quantities? Well, no, the coastal vulnerability model does not account for quantity and quality of habitat, but would you be able to go around by classifying land use differently, like mangrove high quality, mangrove low quantity, with different scores?
Yes, you can absolutely do that. The model is very flexible in that regard. You could provide one input for low density mangrove, another for high density mangrove, and give them different rankings. And then, of course, the model would honor that.
Great, thank you. Another question is there any limitation on the special extent for which the coastal model can process?
No, however, that depends on your computational resources. So many things go into the calculations. The main thing that affects your computation time is the size of your shoreline segments. So if you want to create segments that are very small, maybe, I don't know, 10 meters, it is going to take a very, very, very long time to run this model, and you might not have enough memory or disk space on your computer. So there are more physical limitations just based on the memory and disk space, and not so much a limitation on the model itself. So we have used this model in very small places. We have also used this model on global runs. But when we do global runs, it is a much coarser scale of analysis.
Thank you. So we have another question, which is, what's the difference between nature-based solution and natural habitat?
Well, the nature-based solution, I suppose it may or may not include natural habitat. And natural habitat can exist in a place where it's not really providing ecosystem services. So in this case, we often are thinking about using natural habitat, or I shouldn't even say using, but thinking about natural habitat in terms of a nature-based solution. If we restore some mangroves along the coastline of a community, then that would be considered a nature-based solution to reduce the impact of wind and waves for that community. But the natural habitat may exist there whether there are people living there or not. So I think it's more of an idea of just the biophysical nature of it versus whether we are thinking about it as an ecosystem service.
Great, thank you, Stacie. We have another question, is does the model take into consideration seawalls?
The only place that it would consider seawalls is if you put it in as one of your geomorphology types. So you could have a rocky shoreline, you could also have a seawall, and that seawall may be very effective at reducing the impact of waves. But otherwise, the model is not focused, as I said before, on infrastructure.
Great, thank you, Stacie. And we have another question, if there's any plans to create something similar for riverine ecosystems.
Ooh, not that I am aware of. No, not that I am aware of.
Okay, and then we have another one, is how can InVEST model estimate the cost degradation of the coastal area?
The cost degradation, is that what you said?
Yeah.
So the models themselves usually do not do economic valuation. Usually that is something that's done outside of the model because economic valuation is very complex and it is very case specific. And you usually need a lot of information. So in the case of a coastline, you would need to know what kind of businesses are there, how many people live there, what are their houses made up of. You'd need to know about subsidence and cost of living. I mean, there are so many things that would go into that analysis that we recommend doing that outside of the model. So we take the model results and we may look at the places that are of highest risk and see, all right, who lives there? What businesses are there? Do people make their livelihoods there? And then we would find out information about, how much do houses cost? How much income do people have? How much visitation do they have? And then incorporate that into an economic analysis. If you look through our publications database or our projects database, you'll find several projects that have been done previously, especially I'm thinking about one in Belize and another one on Andros Island, where they did an economic analysis to understand how much, for example, if a certain future occurred so that we had restoration here and development there, how much would that impact the fisheries? How much more or less money would they make? How much more or less tourism would they have? So I recommend looking for these papers, and it will give you an idea of how to do that analysis.
Great, thank you. We have another question, is can this model pull the global habitat data set automatically?
No. Right now, you have to go get the global data sets and put them into the model. We do provide some that come with the sample data, but when you run the InVEST model, it does not automatically go get data. We are actually working on a platform to hopefully do that in the future, but right now it's a manual process.
Wonderful. And then we have another question is, does the model take into account extreme events like hurricanes or tsunamis? And can it tease apart the differences in coastal protection services during ordinary conditions versus extreme ones?
Well, the model does not explicitly think about storm events at all, whether they are small or large. So from that perspective, no, the model does not. One thing that we do know, both on the coast and on land, is that there's only so much that natural habitat can do to protect us. In the event of an extreme storm, there's very little that that mangrove forest can do to help us because that storm is extreme. So the one thing I know they did, now I forget where, I think this was Andros Island, where they had just finished doing an analysis and a hurricane came in. And so what they did there was actually looked at the results of the model, the places that seemed to be of highest risk, and compare that with the damage that was done as a result of that hurricane and see how well the two of them correlated. Right? So again, I'd recommend looking at that, some of those documents to get an idea of how that worked.
Thank you, Stacie. And I think that's it for now. Passing it back to Jessie.
All right. Thank you, Jessie.
Okay, great. Thank you, Stacie and Jade. And now Charlie, research data scientist with NatCap, will present on communicating InVEST results and visualizing data.
Thank you, Jessie. Can you guys see my slides okay? Can you see my slides?
I see a blank white slide.
That should not be what you should be seeing. Okay, let me try again. I've got juggling with several monitors here. All right, can you see it now?
Yes, looks good.
Fantastic. Thank you, Jessie. And hello, everyone. I'm going to be concluding this Intro to InVEST virtual workshop talking about communicating results and specifically a lot of data visualization. So before we jump in, let's talk for a second about why this is so critical. So if you're here today, chances are that you care about nature and people, and specifically making better decisions for people in nature. In general, these decisions are taken by someone, and this someone needs to be informed with relevant knowledge of environmental impacts, trade-offs, etc. That's where we come in. We, ecosystem services analysts, we tend to spend most of our time looking for the best data available and then conducting our analysis, running InVEST models, etc. And then in the last few days before a deadline, we would scramble to put together all our results. But the way we communicate our results really matters because this step, the understanding of the decision maker, is really crucial to actually have any impact. So you've seen this diagram a few times today already. We're gonna now focus on these two last bubbles. But before we start, let me ask you a question. Can we have the first poll question, Laurie? So say you need to gain information quickly from an article, a report, or whatever. When you don't have a lot of time and you need to read quickly through a report, an article, what will you focus your attention on? Will you focus on just reading the intro and the conclusion or the abstract? Will you focus on figures? And you can choose several options. Or will you try to skim through all the text to get a sense of everything?
Wonderful. Thank you, Charlie. And we're going to end the poll in 5, 4, 3, 2, 1. And we're going to share the results.
All right. So a lot of you focus on intro and conclusion, and actually at least half of you, more than half, of also looking at figures. That's a great point. Thanks, Laurie. So actually looking at figures is generally a very smart solution, because 90% of the information our brains absorb comes from visual stimuli. So basically our brains love pictures. And that's why visual communication is extremely powerful. So within our process of reporting, synthesizing, communicating results, especially with our ecosystem services data, where we're synthesizing complex quantitative results, data visualization is really key. So this is why today I'll be giving first a crash course on data visualization, focusing on some key guidelines and recommendations to make good visuals. And then I'll briefly give a few examples of data visualization products we built at NatCap in our NatCap visualization gallery. And finally, I'll share some tools to build your own. So let's get started with our main topic, data visualization principles. Guideline 1, very simple. Know your audience. Indeed, a good visual is tailored to the people who you will use it. So really think, what are their expectations? Graphical conventions and norms exist in each field. What is their level of expertise? You won't talk the same way to academics or governments or hydrologists or a farmer. For example, for an academic audience, I would probably synthesize this map saying something like 3,246 tons per hectare with an uncertainty of plus or minus 20 tons per hectare. But other audiences might prefer something like 10% improvement since last year. So really think about how they're going to use it, and also tailor the visual to how much time they have and what media are they used to. Basically just adapt to your audience so you get your key message across. And that brings me to my second point, also very simple, knowing what key message you're conveying. And it sounds obvious, but before you throw all the data together, all your results, all your InVEST outputs, try to summarize it all in just one sentence. What is your map or your graph or your infographic? What is it saying? And then design it so this key message is really clear. Okay, now let's play a quick game. Let's put ourselves in the shoes of a decision maker, and you're gonna have to make really quick decisions. Decision makers don't have a lot of time to read reports very well, etc. So I'm going to show you a figure for 8 seconds. And at the same time, Laurie is gonna put up a poll, and there's gonna be a question, and you have to answer it. It's about the figure within 8 seconds. Okay, ready? And go. Here's a question, and here's the poll. Who won the presidential elections? Is it candidate A by far? Candidate A, but it's really close? Is it a tie, or is it candidate B? Okay, closing in 3, 2, 1. Results. Okay, most of you found that it's candidate A, but it's close, but some of you thought that it was candidate A by far. So actually a fourth of you thought it was candidate A by far. Now let's play again with a different image. Who won the presidential election now? Oops, can we have, yeah, thank you. Same question, same answers. And 3, 2, 1, let's look at results. All right, I see that most of you who thought it was candidate A by far before now agreed with the majority that it's candidate A, but it's close, and that's the right answer. So these two graphs are actually showing the same numbers. You can see the numbers on top are the same. However, in this first version, the data shown, the size of the chart, is not proportionate to the number shown. So that's called data distortion. And it's kind of misleading. Here we fixed it by adding the 0% baseline. All right, let's play just one other game. This time, you're the mayor of a town downstream from a very eroded area. So you conducted an analysis looking at sediments. So using the SDR model, so the model Ginger presented earlier today, and you ran it for the past 20 years. Now your GIS analyst summarizes results and shows you this graph. In light gray, you see the percent of the population of your town that have access to clean water. In darker gray, you see the percent of the population of your town that don't have access to clean water, so that have poor water quality. You were elected 10 years ago in 2010, and you want to dress a picture of your mandate. Can you say, and that's the question in the poll, fewer people are impacted by poor water quality today than in 2010? Is that true? Is that false? Or do you need more information? Give you a second to think about it. And let's let Lori close the poll in a second.
We'll close the poll in 5, 4, 3, 2, 1, and we're ending polling.
Thank you, Lori. So most of you think this is true. Most of you think that fewer people are impacted by poor water quality today than in 2010. So how about now? I'm showing you this exact same data. On the top left, you can see the same graph I just showed you. I just added the percentages. But on the bottom graph, I show you the data in absolute values. So now you get the full story, and you actually can see that the population in your town increased drastically in 10 years. So now that's a different story, because you can say that the proportion of people with poor water quality indeed decreased. However, there's not fewer people with poor water quality. There's actually more, just because there's a lot more people globally. So that brings me to my third guideline, the concept of graphical integrity. And these images are the original and modified figures I found in different newspapers. And you can see that some figures are misleading, purposely or not, don't always know, but I know we want to avoid this. So to avoid this, respect the true proportions of the data. Don't truncate the y-axis like done in the first example. Provide context, clear and detailed labels, well-known and tangible units that people can relate to, and choose a relevant metric. For example, don't show change in percentages if the absolute total changes a lot, because that's misleading. So overall, we want to design graphs and maps and infographics that show the data truthfully. Okay, one more example now. I think that's my last one. And I think you'll notice that I like to show you examples of bad visualization. I think they're more striking to remember what not to do. This one is pretty extreme. The font is not readable, it's too small, the colors are useless, the data is mirrored, so it's shown twice. This is literally just 5 data points. Let me show you another one, this one. So in these 2 graphs, what's the key message? What is it saying? There's just a lot there. This is what people in the data visualization world would call chart junk. And this brings me to my 4th and last guideline about the data ink ratio. So taking this figure, for example, and simplifying it just to show the data, just reminding us that we're focusing on effectively conveying complex information. And though sometimes some chart decoration can be useful to provide context, in general, it's more disturbing than anything. So what we want to do is maximize the data ink ratio. That is, over all the ink used in your graph, maximize the amount of ink that's used to show data. All right, with these 4 guidelines in mind, I want to talk briefly about colors. Choosing color schemes that are intuitive, because simple design choices will reduce the time spent by your users on understanding the graphs. And all that time saved is time they can use in actually using the data and making better decisions. So for example, intuitive color schemes would be use blue for water, or use qualitative color schemes for categorical data, and sequential color schemes for continuous data, diverging if it's going in two different directions. Also choose color schemes that are coherent. So if you're comparing two maps, they should have the same color scale. So not just the same color palettes. Beware of auto scaling in software like QGIS. If you're comparing two maps, make sure the color scale is actually the exact same. We see that a lot. And make sure also, if you want to be inclusive, and you probably do, you choose colorblind safe color palettes, especially for maps. So for example, avoid red and green. Most colorblinds can't see that. These two resources are great to choose colorblind safe color palettes. So yeah, use colors to encode a dimension of your data. So use colors for meaning. Unlike one more last bad example, this one is really terrible. The same color is used several times for different things. It doesn't mean anything. And side note, pie plots are just, in general, not a good solution. Eyes can't compare more than 6 categories on the pie plot. It's proven. So rule of thumb, just don't use pie plots. All right, let's talk a little bit about some things to consider when making maps. First, do you really need a map? Is the geographical vision adding some value? And oftentimes it is, but think about this. Sometimes a table or graph might be simpler to digest. And then think about the level of complexity you need. So that brings us back to what's your audience and what's your key message. So choose an appropriate resolution, maybe a watershed for water-related ecosystem service, maybe the decision-making unit. And if you have to aggregate, an appropriate aggregation metric, mean, sum, max. Then choose a meaningful unit, something that's going to speak to your audience. Sometimes a simple, like on the example on the right, low to high color, low to high unitless legend is really just fine to get your key message across. And then finally, when comparing maps, consider showing relative changes instead of several maps that the user have to compare themselves. That can really gain also the amount of time they need to digest the map. So that's about it for data visualization guidelines. I just scratched the surface in the short amount of time we have together today, but here are a few interesting references if you want to dig deeper, and they will, my slides will be shared, so you'll get all these links on our website, as Jessie said afterwards. So one that I'll dive in a little bit more today is this website, viz.naturalcapitalproject.org. Because that's our visualization gallery at NatCap, and we also built there a toolbox to guide ecosystem services data visualization. Which brings me to my second section, where I'm gonna go actually, can you still see my slide though I switch software? Yes. Fantastic. So you can go to that URL yourself, viz.naturalcapitalproject.org. I'm just going to briefly point out, I just mentioned this toolbox, which you can read online. There's a lot of examples of different design strategies to display specifically natural capital type of data, invest outputs. And for each of the main display tasks you would get with the type of data we deal with, there's some examples you can explore, etc. So yeah, but going back to our visualization gallery, we have here quite a few examples of some of the work we've done at NatCap or some of what our partners have done. I'm just going to briefly show a couple. Maybe this one. This is a project we conducted a couple years ago in Myanmar. So it's a national scale ecosystem services assessment. And here we summarized results per type of ecosystem service in a story map way. So that makes it very readable and very nice for several type of audiences to just explore our results and abilities to play around the maps. I'll let you, all of these I'll just really briefly skim through and let you explore, dive in more on your own if you want. Then let's talk briefly about this one. This is this time a global scale assessment we conducted recently of 3 ecosystem services. And here we summarized results at different scales. So we were talking about resolution and what's the appropriate resolution to summarize results. For example, for this one, most policymakers were really interested in country level summaries. So we summarized results at the country scale with, you can see pretty intuitive units, such as number of people exposed. But we also allow for exploration of really fine scale resolution data and results, because this is really a strength of this analysis. And here, interactive data visualization really plays an important role, because it wouldn't be possible to show that amount of data at such a fine resolution on a printed map. So I won't show you all of these examples, because that would be a whole webinar on its own. But I noticed we have quite a few Spanish speakers in the crowd today, so you might be interested in this project. We're still conducting, actually. We close to finalize in the Amazon. And maybe another one I'd love to point out is this one, because Stacie just introduced the coastal vulnerability dashboard. So this is a very helpful, the coastal vulnerability model. And this is a very helpful tool, the coastal vulnerability dashboard, where you can directly load your InVEST outputs, and it allows you to visualize them spatially. So it's, yeah, it's really nice and simple to use. All right, I'm running out of time because I'm speaking too slow, so I'll definitely let you explore those on your own time. And I'll now talk for a minute about tools. I get asked a lot, what is my favorite data visualization tool? And the answer is, it depends. And I know that's not the favorite answer, but there's no magic solution, or there's no one size fits all. So here's a definitely not exhaustive flowchart of data visualization tools I use and I would recommend. These are all free and mostly open source. And I would say it really depends on your level of expertise. So do you code, or do you want a solution where you don't need to code? Do you need interactivity? Also depends on how custom you need your visual to be and what's your data. So if you have a lot of maps. So yeah, these are a few libraries and tools that I use very often and that I highly recommend. They go from the most classic charting and mapping tools like QGIS here on the right, to more interactive custom coded solution like JavaScript libraries such as D3 or Leaflet, which are really powerful. These libraries are actually the basis on which all the examples I just briefly showed are built. The one thing with these custom interactive dashboards is they're quite time consuming to build. So here's a thing I'm really excited to be able to share with you today, because it's a product we've been working on for a little bit, and it's still quite preliminary. It's a beta version, but it's the first time we're showing it officially. So from the motivation that interactive dashboards are useful to decision makers in understanding these type of complex results and maps, but that they're quite time consuming to build, we thought we could try to make this a lot easier. So this is a template to build your own interactive visuals. You can see the demo at this link, this.naturalcapitalproject.org/viewer template. And if you want to try using it with your own InVEST results or your own data, please clone the second link at the bottom of this page. So you don't need to be able to code to use this. You just need to be able to read code and have some basic knowledge of, for example, using GitHub. So yeah, that's our gift to you. It's super new. I would love to hear your feedback on it. I would love also to see what you create with it. So please send us a link so we can feature you on our NatCap visualization gallery. And that's about all I have for you today. I'll answer questions if I'm not too much over time. Jade, do people have questions?
Yes, good job, Charlie. One question from Helena. Is there any metrics to quantify the impact or incidence of results presentation with decision makers or other types of audience?
That's an excellent question. Thank you. Yeah, thank you for asking that. I've actually asked myself that question quite a lot when I was building all these, because it's time consuming. And we recently conducted research. It's available as a preprint. It's not yet, it's in the peer review process. Actually testing these dashboards and testing how decision makers gain insights. And if using these dashboards versus classic reports actually help them better understand these results and make better decisions. And our conclusion is yes, it does. We conducted both quantitative and qualitative analysis over dozens of dashboards, and it proved pretty successful. So I don't have a good number to quantify exactly how much. We weren't really able to do that, but we were definitely able to prove that it was worth our time.
Thank you, Charlie. I think for now, that's it for all the online questions, unless there's more that haven't come through.
Cool, then I'll probably give the mic back to our great host, Jessie, to close it up for the day.
There's one more question that came through.
Yeah, take it.
Is how, I'm not sure what HIG is. How is, yeah. Oh, hi, thank you. Is the actual interaction of decision makers with dashboards.
How high? I understand the words. I'm not sure what you mean by how high.
So I guess is how decision makers use those dashboards. Do they use them frequently or? Yeah,
that's it. Okay, do they use, okay. Okay, that's a really good question. Sorry, David, it took me a while to get that. Yeah, so for the couple dashboards where we actually took the time within the project to really evaluate how they were used and how they impacted, we actually found that people would go back to them quite frequently. And because they know it's here, they actually use it as the main resource even to go download the data. And we had to also think about it as sometimes a portal for the project, because that's the first place they would go to when they would look for data or even the report. We also found that when we start building the dashboard mid-project, so before we have all final results, that actually fosters more interaction where we get feedback on both how to present results, but also results quality. And that allows us to iterate, which is very important in the NatCap process, that allows us to really iterate a lot more. And then, you know, we ping them when we updated with newest data, and we kind of get this feedback loop very, very frequently. We also found, I think Stacie mentioned that briefly talking about hurricanes. One of the viewers, I think it's this one, the Bahamas hazard viewer, you can find on our visualization gallery, that one of my colleagues built a couple years back for a project using the coastal vulnerability model. The partners actually emailed us again when they had a hurricane coming, I think it was just last year, to go back to this viewer, to go back re-exploring the results in the new context. So that's definitely something they also remember playing with and using, and that's definitely something they go back to. Yeah.
Thank you, Charlie. Another question came through. What software for visualization design would you recommend for academic publications?
You're not gonna like my answer, but my answer is gonna be, it depends. And here's an ugly flow chart to show you what to do. In general, for my academic publications, I'm a Python person, so I would use the Python libraries built on top of Matplotlib, Seaborn, etc. But there's the equivalent with ggplot, etc. in R and in many other software. One recommendation that I would have, not just for academic publication, but for any pretty publication you want to do, is make your plots or your map in the best appropriate software for a map, maybe QGIS, or you can make it in Python or whatever, and then bring that in Illustrator, if you have Illustrator, or PowerPoint, or even Google Slide, like all these software that help you really place things prettily and do things manually. It sounds really bad from a data scientist who likes automating everything, but it really actually saves time and make better looking figure to actually export them in a illustrating software after your plotting software.
Thank you. And here's another question. Are those dashboard visualizations done in JavaScript?
All the web-based ones, so all the examples I showed today and most of the ones you'll find in our interactive visualization gallery, yes, they're JavaScript based, and mostly they build on Leaflet, which is the mapping library, and D3 for charts.
Thank you. And there's oh, and I got another question just came through, and I guess that's maybe for the larger team. What method can we use to assess impact on biodiversity loss based on forest-based products consumption by an urban area?
I would probably look into the habitat quality model for this one. You can find it online and go through the user guide. That would be my gut feeling. I don't know if others have other thoughts.
I would probably say the same thing, but the model is very simple, so it would be a lot of work outside of the model for you to make that connection between the consumption of the urban area and the impact on biodiversity. So like that's actually a really complex question, and our simple models may be able to give you some input to that, but you're going to have to do a lot of work outside of it to figure out where those products come from, how they're being harvested, and all those kinds of things.
Thank you, Stacie. I think that will be it in terms of Q&A, so passing it back to Jesse.
Great.
Thanks, everyone.
Yes, absolutely. That was great. Thank you, Charlie, and all our presenters. It's time to wrap up. So we'd like to remind you to please enroll in our 2 upcoming InVEST virtual workshops, where we'll take a deeper dive into specific models. Freshwater Quality Model with Ginger is on August 4th, and Urban InVEST with Roy is on August 18th. Please take NatCap's massive open online course, or MOOC, if you haven't already. Like this webinar series, it's free and available at edx.org. That's edx.org. The course introduces NatCap's approach to using ecosystem service information to inform decisions. It uses specific examples to illustrate how the approach has worked in each case and highlights key methods and tools used in implementation. The InVEST User Guide is an invaluable resource for learning not only about the science and theory behind each model, but also how to use them. Access it through our website, where we have English, Spanish, and Chinese versions. Each model's chapter contains important information, such as an explanation of the science methods and equations behind each model, input data requirements, a description of each model output, and global data sources. So be sure to read the user guide carefully before using a model, then use it as your first resource for answering questions. And please do participate in our community forum. If you experience any issues while using InVEST, you should always check the user guide first. But if that doesn't help, consult the forum. Find it at community.naturalcapitalproject.org. Search to see if your issue has already been posted about by another user. If your problem is novel to the forum, you can create a new discussion and get assistance from NatCap staff and the wider community of users. When posting with an issue, please remember to upload your log file if one was generated. It's a plain text file, and so it'll have the .txt extension. And definitely please visit Charlie's awesome NatCap Data Viz website at viz.naturalcapitalproject.org. That's viz.naturalcapitalproject.org. Visit our website, naturalcapitalproject.stanford.edu. There you'll be able to sign up for our newsletter, find our publications, and explore where we work. And please do follow us on social media. Our Twitter handle is @NatCapProject, and feel free to email us anytime at investsummer2020@gmail.com. Lastly, please don't forget to take our post-event survey, which you'll be directed to after you leave the webinar. Thank you so much for attending, and we hope you'll join us again on August 4th.